All right, so section 6.2 is on definite integrals and Riemann sums. It's actually Riemann, in very throaty German. Okay. So George Friedrich Bernhard Riemann studied under Carl Friedrich Gauss. Remember, these are the German names. You guys can say it. And came up with a rectangular method of approximating. We've learned that we can use what's called right-hand and left-hand sums. Okay, these are Riemann sums. Okay. You can also use the midpoint rule. So this guy actually found out that you can use anything. So you can use anything on that interval, and summing all those together would be a Riemann sum. So back when I took my AP test, there was a question, and it said, find the Riemann sum. And I had no idea who Riemann was. So I had no idea what I was supposed to do, because I didn't know what his name was. So that's why I'm telling you this guy's name. He's very important. So that stud there, Riemann, you'll remember that for your AP test. It's just a rectangular approximation. So right-hand sum, left-hand sum, some kind of sum. All right. So I was going to skip number 1. But since you guys are saying that you're having trouble with your number 10, maybe we should do number 1. It's kind of a review of last time. All right, so it says consider the region bounded by the graph of f of x equals square root of x and the x-axis on the interval 0 to 1. Okay, so first we draw it. Oh, I need to orient my thing. Okay, so let's draw. Okay, so what we're trying to find is this area between 0 and 1 under the curve and between the x-axis. Okay, and I told you to evaluate the limit. This notation is just like you had last time, so the limit as n goes to infinity, so we have an infinite number of rectangles, f of ci times delta x. So the height of each rectangle times the width of each rectangle. And it says where ci is the right endpoint of the partition, given by ci equals I squared over n squared. Okay, this is different than what we did yesterday because now we're not using the same width. Okay, do you guys want to do it this way or do you want to make them equal widths? It's up to you. I'm guessing I did it this way because it's probably easier this way. So, yeah, I'm guessing that since we have the square root, we're making it I squared over n squared for a reason. All right, so here's what's going on. So the first one, C1, that's going to be at 1 squared over n squared. So it's going to be 1 over n squared. So somewhere around there. Okay, C2 is going to be 2 squared over n squared. So it's going to be 4 over n squared. Okay, what's the distance between those two hash marks? So what's the difference? 3 over n squared, do you guys see? It's not always going to be 3 over n squared. Do you guys see that the width of the first rectangle was 1 over n squared? The width of the second one is 3 over n squared? Okay, they're not going to be the same. All right, so the next one would be C3. That would be 3 squared over n squared, so it would be 9 over n squared. So then it would be 5 over n squared. You guys see the pattern that's going on here? Okay, so the width of the rectangles, that's the ci minus 1. So it's saying take the ith mark and subtract out the mark before it. Okay, well ci would be I squared over n squared, and then ci minus 1 would be I squared minus, I minus 1 squared over n squared. So we simplify. Makes sense? All right, so when I FOIL everything out, I'm going to have I squared minus I squared. I'm going to have plus 2I and then minus 1. Do you guys see that? So I'm going to have 2I minus 1 over n squared. Do you want me to write it out? All right, so that's my width of my rectangle. So when I come up with my sum, So S for sum. It's going to be, but then you distribute the negative, so it'd be minus then. Okay, let's not do the limit part. I won't make you write limit all the way through. We'll just do it at the very end. So let's do S equals the sum from I equals 1 to n of my height. So this is why I wanted you guys to use this one, the I squared over n squared. Because now when I plug it into my function, what happens? It's I over n. Do you guys all see that? So you can write that out if you want, but I'm just going to write I over n for my height times the width. So 2I minus 1 over n squared. Just so you guys could see that the width was changing. Yeah, you don't always have to do that. But I think sometimes it helps with actual numbers instead of i's and n's and k's. All right. Okay, so now that we're here, it's not going to be too bad to simplify. So I'm going to multiply through. So I'm going to get the summation from I equals 1 to n of 2I squared minus I all over n cubed. And then we know we can bring the sum in to the two pieces, and I'm going to bring the n cubed out front. So what I'm going to have, well, I'm going to bring a lot out front. I'm going to have 2n cubed out front, the summation of I squared minus 1 over n cubed, and then the summation of I. Does that make sense to everyone? Yes. So if you'd written out all the terms here, so if I was writing out all the terms, I'd have 2 times 1 squared minus 1 over n cubed plus 2 times 2 squared minus 2 over n cubed plus, and so on. So they all have an n cubed in common. So that's why I pulled the n cubed out for both of them. And then I'm also rearranging. So I'm taking all of these first. So I have 2 times I squared. And then I'm taking all the other pieces. So minus 1, minus 2, minus 3. That's the minus I part. Okay. All right. So it's 2 over n cubed times, do you guys have the I squared thing memorized yet? N. Yep. You guys are good. Better than me. I always forget that one. Both of them? See, I told you I forget them. Okay. All right, so 1 over n cubed times summation for I, that's like the Gauss formula. So 1 plus 2 plus 3 plus 4 would be the number of pairs, so n over 2 times the first term plus the last term. Okay, simplify down. N and n cubed cancel. I'm going to FOIL out the top, so I'm going to have 2n cubed, or 2n squared, plus 3n plus 1 all over 3n squared, minus n cubed and n reduced down to n squared. So I have 1 plus n on top in parentheses all over 2n squared. Okay, and then bring the denominators in each piece. So it's going to be 2/3 plus 1 over n plus 1 over 3n squared minus 1 over 2n squared minus 1 over 2n. So at this point, if you guys just want to say like area equals, you can, because in your head you're taking the limit as n goes to infinity. So this part would go to 0, this part would go to 0, this would go to 0, and this would go to 0 if n was a huge number. So your area is 2/3. Make sense? I also cheated and I showed you the shortcut yesterday, which I really shouldn't show you the shortcut before you learn all this, but I'm such a nice teacher that I decided to. So the shortcut was you have the square root of x and you're going from 0 to 1. So what do you take the derivative of in order to get the square root of x? That's a hard thing to ask. It makes it easier if you think of it as x to the 1/2, right? So what do you take the derivative of in order to get x to the 1/2?
2/3 x to 3/2.
That's exactly right, yep. Going from 0 to 1. So plug in 1. So when I plug in 1, I get 2/3. When I plug in 0, I get 0. So it's 2/3. Much quicker. All right. So we're feeling better about the infinite sums? No, on the AP test, I was so mad after I found out who Riemann was and what the rule was on my AP test, because it was just find the Riemann approximation with n equals 4 or something, with like 4 rectangles. But I didn't know what the Riemann approximation meant. I didn't know it was like the rectangular method. So, okay. Okay, next thing. So definite integral. So it says for any function f defined on a to b, the definite integral of f from a to b looks like squiggly line. So the elongated s. It's called an integration sign. Is equal to an infinite rectangles, right? Like the infinite rectangle method. Okay. It says it is the same for any choice of evaluation points. So any, like you can use right-hand endpoints, left-hand midpoint. You can do something like we just did on the last one. You can use any point on those rectangles. We say that f is integrable on a to b. Integrable. Integrable. All right, so for the midpoint rule, the choices of CI are in the middle of the interval. So we haven't done that yet, but we're going to do the midpoint as well. Okay, so it says for f of x equals sine of x on 0 to 2 pi, give an area interpretation. A sketch may help. Okay, so we know that sine goes up and comes back down. Here's pi. Here's 2 pi. And let's say we were talking about like pi over 2. What would f of pi over 2 be? 1, right? That's the height. So that rectangle would have a height of 1. It'd be multiplied by the width of whatever the interval was. What is f of 3 pi over 2? -1. So what do you think that the limit as n goes to infinity of I equals 1 to n of f of ci delta x is? 0. Why'd you say that, Mackenzie? Yeah, because you had positive y values for your heights of your rectangles, and then you had negative heights. Very strange. So they would end up canceling each other out, so this would be 0. So if I did the integral from 0 to 2 pi of sine of x, we always write dx to say that we're taking the antiderivative with respect to x. Later on in calculus, you use multiple variables, not in this class, but later on, like calc 3. Mackenzie has a look of fear. Okay, so this would end up being 0. Okay. So what's important about this is I don't want you guys to think that taking the integral of something is always going to be the area of something. A lot of times we'll say find the area between the x-axis and this curve, and the area isn't 0. Area is always going to be positive. So you would need to find the area here and find the positive area here and then add them together. So later on in like our next chapters, we're going to be doing that. But on this chapter, you're always going to have your f of x is going to be above the curve, or above the x-axis, I mean. It's going to be positive. Okay, so we're not going to have to worry about that. Okay, so number 2, so use the midpoint rule with n equals 5 to approximate the integral from 1 to 2 of 1 over x dx. Okay, so it says recall the symbol dx always goes with the integral sign. The expression 1 over x dx means find the area between the curve f of x equals 1 over x and the x-axis from the points 1 to 2. So like I was saying, this is only because our curve is above the x-axis. If it goes below, saying the area is kind of tricky. All right, you can use any variable. You could have 1 over x dx. You could have 1 over r dr. You could have 1 over t dt. These would all be the exact same value. They mean the same thing. So you can use any variable that you want. It doesn't always have to be x. And the AP test uses weird variables all the time, so don't be surprised. Okay, so what this means, here's what 1 over x looks like. Yes, part of it does go below the x-axis, but not the part that we're worried about, right? It's going from 1 to 2. Okay, we want 5 rectangles in there. So my width of my rectangles, delta x, is always b minus a over n. It's saying your whole interval is 2 minus 1. It's a length of 1, and you're going to divide it into n pieces. So in our case, n is 5. So I have 1/5. Now you shouldn't really memorize that formula. This should just make sense intuitively. So the first one's going to be like 1.2, right? 1 and 1/5. Then I'm going to have 1.4, 1.6, running out of room, 1.8. Those are all supposed to be evenly spaced. Okay, but I want to use the midpoint. So what's the point in between 1 and 1.2? 1.1, right? So you're going to have to go to the center of this rectangle, or the center of the strip, and that's where you draw your height. Okay, so what I usually do on this midpoint rule is I'll draw out the interval, and I'll divide it into its pieces, so 1.2, 1.4, 1.6, 1.8, and then I'll draw like marks in between. So I'll say, okay, well, what I'm really finding is 1.1, 1.3, 1.5, 1.7, and 1.9. Okay, that's going to be the height that we're using. Yes? Why? Because we want our rectangle to be, if I zoom in here, it will make more sense. Let me kind of draw it again. So say this is 1 and this is 1.2. We want the height of my rectangle to be in the middle, like that. Now, what would be the advantage of using the midpoint? Yeah, and like in this case, a little bit of your rectangle is above the curve and a little bit's below the curve. So it's going to be an even more precise method. Okay, so that's why we'd use the number in between. Okay, so my area, so if I'm approximating 1 to 2, 1 over x dx, it's going to be the width. So what's the width of each rectangle? Yeah, 0.2 or 1/5, right? So it's going to be 0.2 times the height, so f of 1.1. So if you guys want to put in 1 over x into your... It really wouldn't be bad if you think of it like fractions, but we'll do that. Ew. Okay, I'm just going to leave it as 1 over 1.1. That's nicer. Because I got a decimal that was repeating. I got 0.90909090. Okay. Yeah. So let's just leave it like 1 over 1.1 when we're actually putting it into our calculator. Okay, so then I'd have 0.2 times 1 over 1.3 plus 0.2 times 1 over 1.5. So it's always the width times the height.
Is it 1 over 1.1?
Yeah, because your original function was 1 over x, yes. All right, so on those you can pull out the 0.2. Anybody get an answer? Yeah, that's what I got too. 2. So 0.692. Okay. The interesting thing about this one is you guys probably don't know how to do the shortcut method on this one yet. We would talk about this yet. Because this is x to the negative 1. So it's like, how do I do the antiderivative? Yeah, it'd be like x to the 0. That doesn't make any sense. So what do you take the derivative of in order to get 1 over x? Natural log, that's right. So it's going to involve natural log. But actually for antiderivative, it'd be natural log of the absolute value of x. Because you can't have negative x's. So it's very strange. All right. All right, so the definite integral of the area of a region. So the area would be given by, so notice how it says f is continuous and non-negative, so it's above the axis on the closed interval a to b. Then your area is given by the integral from a to b of f of x dx. And again, you guys still haven't really technically learned the shortcut method, so we're going to do some other stuff with it. All right, so it says evaluate the Riemann sum for f of x equals 4x minus x squared, taking the sample points to be the right endpoints from 0 to 3 with n equals 6. You guys did this a lot on your homework. Are you guys good on 6 rectangles? Can we skip this one? Yeah. All right, that's basically just saying use 6 rectangles, use right endpoints. Okay, so sketch the region corresponding to each definite integral, then evaluate using a geometric argument. So basically we're going to look at the picture and we're going to figure out the area. It will be pretty easy. So this first one, 6 is my function. That's the same as y equals 6, right? So here's my function. My limits of integration, when I said limits of integration, that's 3 and 7. So I'm going to start at 3 and I'm going to go to 7. So I'm saying find the area under the curve, y equals 6, between 3 and 7. So find that area. Easy enough. Height of 6, width of 4. Your area is 24. So in this case, using the drawing was a lot easier than doing that shortcut method that I taught you. Okay, next one. So I have x plus 4. X plus 4 is a line with y-intercept of 4, slope of 1. You're going to go up 1, right 1, up 1, right 1. We're finding the area below that curve, so in between that curve and the x-axis, not curve, but line, from 0 to 3. So what shape is this? A triangle on top and a rectangle below. You could do that. Or what is that called? Look at it sideways. A trapezoid. So section 6.5 or 4, I can't remember what your last section is. That's using what's called the trapezoid method. So it would use trapezoids that are on their side like that. Okay, so your area is going to be 1/2 the height. So height is the distance between the two bases. So h is 3 times b1 plus b2. So a equals 1/2 of 3. b1 was 4. b2 was 7. So you get 16.5. Because I started at 4 and I went up 1, right 1, up 1, right 1 3 times. So that should be a height of 7. Okay, the next one's a little bit harder. Do you guys know what shape this is? So if y is equal to the square root of 4 minus x squared. See how if you square both sides, you get y squared equals 4 minus x squared. So you'd have x squared plus y squared equals 4. Now what shape is it? A circle. But we only had the positive square root part. So do you guys remember when you graph circles in your calculator? Have you done that before? You always have to do the positive square root and the negative square root. So what you end up getting is a circle with radius 2, but it's only a semicircle. It's only the top part. So this area is going to be half of the area of a circle. So 1/2 pi r squared. So 1/2 pi, my radius is 2, so 2 pi. Oops. Make sense? So you're integrating, you're doing this antiderivative thing, but you're not really doing the antiderivative at all, right? You're looking at the graph, you're realizing that it's a certain shape. So that's what this whole section is about. So on the homework, you're just drawing things, figuring out that it's a triangle. I mean, it's really not hard. It's like a geometry assignment. All right, so if f is defined at x equals a, then what would the integral from a to a be? 0. Why? There's no width, right? So there was no rectangle there. It was just a skinny little not there line. Dotted line, kind of. All right, number 2. So if f is integrable on a to b, then we define the integral from a to b of f of x dx to equal negative the integral from b to a f of x dx. Okay, that one's very strange. Really, I mean, if you think of the shortcut method, it totally makes sense. Like you're saying, take the antiderivative. So we usually do capital F. So that would be capital F of b minus f of a for this one. Well, if I did a on top and b on bottom, then it'd be the opposite. It'd be capital F of a. So capital F means antiderivative. So it'd be capital F of a minus capital F of b. Well, that's the opposite of what we had before. So do you just put a negative out front? Okay, so when you think of it that way, I think it makes sense. Really what you're thinking of with the rectangle method is if you went from 2 to 5 originally, and then all of a sudden you're going from 5 to 2, your widths would be negative. You'd be going backwards. It's very strange. So I would probably think of it with the shortcut method. Okay. So if you see something strange that says like 6 to 2, you know the bottom number should always be the smaller number. So just know that that's going to be the same as the integral from 2 to 6 with a negative out front. Okay, additive integral property. So it says if f is integrable on the 3 close intervals determined by a, b, and c, then if I was going from a to b and finding my area, and then I was going from b to c and finding my area, that would be the same as going from a to c. Good. Because it's the same curve that you're under. Okay. Properties of definite integrals. These are very similar to the sigma method that we did. So think about all the things you can do with a sigma. You can pull the sigma into a sum, right? You could pull a number out from the sigma because that number would be multiplied by everything. So it's like the reverse distributive property. You're factoring it out to the front. You know what I'm saying? So on this first one, if I have a number out front, I can pull that number to the front of the integral sign. So what I'm saying is it's just like if I had like 5i with my sigma, we pulled the 5 out to the front. Because every single thing, that would be like 5 times 1 plus 5 times 2. Every single thing has 5, so you can factor it out.
And then you multiply it back in at the very end.
Okay, so the next one, if I had a sum, remember if I had I squared plus I, we could bring the sigma into both pieces and we'd write sigma I squared plus sigma I. So really this elongated S sign is a shortcut for writing limit as n goes to infinity of your sigma sign, I equals 1. I mean, it's much easier to write it this way. All right, so I have a to b f of x dx plus a to b g of x dx. One of my big pet peeves is when you guys leave off the dx. So don't do that. It's a break time already. All right. All right, so number 1 says use your result from 2b above to evaluate the integral from 0 to, or from 3 to 0. Okay, so we just found that in b. We found it was 16.5 using that trapezoid. So what's the answer going to be? Negative 16.5, right? 2? 0. And then 3, we're going to use a graph. The absolute value of x looks like this. We're going from -1 to 1. So we're finding the area of these two triangles. They're actually the same area. So that's basically like saying you have 2 of the integral from 0 to 1 of, you could just say x dx if you really want to. If you want to leave the absolute value, that's fine. All right, so what's the area of this triangle? So it's 1/2 base times height. The height would be 1, makes sense. Absolute value of 1 is 1. All right, so that's 1/2, but I have 2 of them, so 2 times 1/2, so you get 1. Yay, geometry. Okay, so the AP test likes to do things like this, where they'll give you like lots of different things. Obviously, they wouldn't look like x squared because you can actually do the shortcut method, but they'd say like the function f of x integrated from 1 to 4 is equal to 18, and this one is something else, and you have to like add them or whatever. Okay, so suppose you know the integral of from 1 to 3 of x squared dx is 26 over 3. The integral from 1 to 3 of x dx is 4, and the integral of 1 to 3 of dx, so 1 dx, is 2. Use these to evaluate the sum. So basically what we're going to do is we're just going to bring the integral sign into each piece. And then remember, you can bring numbers out. So this is really a negative on the outside, 1 to 3 x squared dx, plus 4, 1 to 3 x dx, minus 3, 1 to 3 dx. You can write 1 dx if it bothers you. So it's a negative times, this whole piece was 26 over 3, plus 4 times, someone's hungry.
Yes.
So 4, I did.
It was
I had to eat some fruit snacks while you guys were on break, so. All right, and then the last one is, oh yeah, did I do it? No, 4 times 4, okay, and then negative 3 times 2. Your tummy's growling too much, you can't understand it.
Wait, so we combined? Oh, because it gave us what they were.
Yeah, you were given that the integral from 1 to 3 of x squared dx was 26 over 3. So I just plugged that in. So I have negative and then 26 over 3. All right, so your answers, 26 over 3 plus 16 minus 6, 4/3. So your answer is 4/3. Okay, graph ones. So it says the graph of f of x and g of x are shown below. Use them to evaluate the following. So if I was going to evaluate the integral from 0 to 3 of f of x plus g of x, I could pull it apart. So from 0 to 3 of f of x is just going to be a little triangle. That triangle is right here. So it's 1/2. The base was 3. The height was, I don't know what it was. I drew over it. Ooh, it didn't go very nicely. Oh, no, it does. Right there. 1, 2, 3, 4, 5. plus the integral from 0 to 3 of g of x is this taller triangle. So it's 1/2, base is 3, height is 8. So I get 15 over 2, so 7.5 plus 12, so 19.5. See how those work? That's a 5, it looks like a 3.
Wait, what's the 3 for?
You're always doing like the area of the triangle is 1/2 base times height. So your base was 3.
Oh, so we go across 3.
Yeah. All right, so the next one, a little bit harder.
What's that to the far right, the 1/2 times 3 times 8?
Yeah, 1/2 times 3 times 8. Yeah, our projector's messed up. It's widescreen now. I don't know why. I just go with it. All right, so the next one, so this is saying just from 3 to 7. So 3, 4, 5, 6, 7. Okay, and so f of x would be, you can kind of draw in the shape, a trapezoid. So it's 1/2. The height of the trapezoid is just the distance between the two bases. So it's 4. B1 and B2. So the first one was 5 and the second one was 5, 6, 7, 8, 9, 10, 11. Did you guys get 11? I hate those little grid lines. All right, and then the next one. So it's going to be minus 1. Well, I don't know if it's 1/2 yet or not. Let's see what the shape is. So g of x from 3 to 7. 5, 6, 7. Oh, I'm doing the wrong one still. I'm doing the other one. I was like, isn't this what I just had? Okay. Yeah, it's a rectangle, right? So it's 4 by 8. So 2 times 16, so 32 minus 32, so it's 0. So those two areas were exactly the same. Yeah, it does make sense if you look at it. Do you guys see how this little corner here was the same as this little? So that's what happened when you subtracted the two things. All right, so if the region graphed is below the x-axis, the f of x values when computing the area of each individual rectangle is negative. This creates a negative area, quotation marks. So if you ask for the area of a region where part of it's below the x-axis, you have to change the sign to positive. So basically, like what you would need to do in order to do this is if you had something that went above and then below, if I really asked for the area is always positive. So you would need to find the integral from here to here, and then subtract out, so add the opposite of this part. Okay, so we have some examples.
Wait, can you add the opposite and just subtract or add the opposite and then add it?
You can subtract, yeah. So you just subtract out the other part, because the other part's going to be negative, so you'd add on a positive number then.
So you'd end up with a little number for that one.
Nope, you'd end up with a big number.
So you do it. Because you're subtracting.
Yeah, it's like you take the absolute value of both and then add them together.
Okay.
Does that make sense?
Yes.
Okay, so it says, in other words, the area from A to B of f of x dx is the area above the axis minus the area below the axis, because this would actually be a negative number. And this is a positive number. Yeah. All right, so if I'm finding the integral from pi to 2 pi, so right here, I'm not asking for, ooh, what did I do here? Yeah, this should be negative in the end. I have something wrong here. This should say the area. This should not be an integral. This needs to say the area. Because you can't have a negative integral value. It happens. Okay, so we're finding what the integral is from there to there. So it's going to be a negative number. So when I compute this, pi to 2 pi. Ooh, we don't know the shortcut yet. No, I mean, I showed you the shortcut. You guys could find the antiderivative of sine, right? What would it be? Negative cosine, and then you can plug in those two values. So I think I have something wrong with this page. I don't think I can teach you this yet. Okay, I'm going to skip it. So we'll skip this page. Might go back. Okay, so constant functions are very simple to integrate. Draw a sketch that represents the integral from a to b of cx dx. So c would be the line y equals c, and then you go from a to b. So your area, let's say c is a positive constant. So your area would be height times width. So it would be c times b minus a. Okay. This is what I wanted to do first before we went back to the other one. So it says numerical integrals or definite integrals can be computed using a calculator. Okay, so that probably tells you that most of the things on the AP test are what we call indefinite integrals. So they're not going to have numbers, or it's going to be on the non-calculator section. So you're going to have to still do this by hand. So in years past, I teach integration, so that shortcut method that I kind of showed you. I do that for a month or so before I even teach you this calculator method. But this book likes to teach it to you early, so we're going to go ahead and I'll teach it to you early this year, and we'll see what happens. Hopefully it doesn't destroy your, confidence, I guess, and you guys will still do it by hand. Okay, so see the graph below. So shade the area represented by the integral from 1 to 3 of 4 over 1 plus x squared dx. So if I was going from 1 to 3, it would be this area right here. Okay, you can find this area by using the setup on your calculator. You're going to have something called FN int. So that stands for definite integral. Finite integration, another way. You can find this with Math 9. So I'll often call it Math 9. Last year I talked about Math 9 for about 3 months, and then I used that term one day, and Kwame said, "What's Math 9?" The whole class was like, "Oh, Kwame." You like to sleep a lot. All right, so then you put your function. So you do 4 divided by parentheses 1 plus x squared, so you know that whole denominator, that whole thing is in the denominator. Then you do comma, x, and your x values go from 1 to 3. So it's very similar to the inderiv that you guys did. Okay, so when you guys do that, what do you get? Yep, so that's the area that's under this curve. If you kind of try to approximate, see how this looks like 1, that looks like 0.855 about. So you can usually tell. Okay. Okay, so however, sometimes students make simple mistakes with this. So I've told you that sometimes you're going to have integrals that switch above and below the axis. So for instance, here's a sketch of y equals x squared minus 5x plus 4. If I asked for you to compute the area between the curve and the x-axis from 0 to 3, you would find this positive number, and you would subtract out this negative number. So you would find 0 to, is that 1? Yeah, 1 of f of x. I'm just going to write f of x dx. And then you'd subtract out the other one, because the other one's going to be a negative number. So it would be from 1 to 3 of f of x dx. So all of this was a negative. All of this was a positive.
Wait, why are you finding this on
Why am I doing what?
It's on the outside of the curve.
It's on the outside of the curve?
Yeah.
What do you mean?
It's not inside the curve.
It's the area between the curve and the axis.
Yeah, it's always just between the two things, yeah. So the x-axis and your curve, it's the part that's sandwiched between them. And then those two x values, so from there to there. I see what you're saying. So you were thinking like inside the parabola. Is that what you're saying? Like you thought it should have been like this part? Yeah, it's always the part that's in between the x-axis and the line, the curve. Okay, so compute the integral from 0 to 3 and then compute the integral broken into two pieces. Are they the same? So if you guys actually do the integral from 0 to 3 of x squared minus 5x plus 4 dx, see what you get. So you can do your math 9. X squared minus 5x plus 4. And then x goes from 0 to 3. You end up with negative 1.5. Did you guys get that? Yeah. Okay, now let's do the other one. So let's do from 0 to 1 of x squared minus 5x plus 4 dx. So what you guys could do is you could do second enter, and it pulls up that last thing that you just did, and then change the numbers, right? So now go from 0 to 1.
Wait, how would you get something different?
Okay, this part ends up being 11/6. And then do second enter. You might have to do it a couple times if you change that to a fraction. And now go from 1 to 3. And this one you get negative 10/3. So when you do 11/6 minus a negative 10/3, you with me? You get 31/6. 31/6, not 0.6. Okay, that's like 5.167, somewhere in there. All right, so why are those different? What's the difference between the two different things? So when I say find the area, how's that different than the integral from 0 to 3?
Because the area is like absolute value.
Yeah, your area includes only positive areas. So you find this positive area, and then you find what this negative quote marks, area is, but you're really like taking the absolute value of it. You're making it positive because you're subtracting out the negative number. So you're adding on a positive number. So when you say find the area, that's not just the integral from a to b. You need to consider if it crossed the axis or not. Okay, so on your homework problems, I'm guessing that they're all positive, but I wanted to say that. So now if we go back to the part that I kind of skipped. So you guys can do that now that you have math 9. So if I do the first one, math 9, I'm going to do sine of x, comma, x goes from pi to 2 pi. See how when you do this, you get a negative number. So negative 2. You got what?
Quit.
Did you forget like an x or something? So it should say,
Do I put it in parentheses after sign of x?
Yeah.
Oh, I forgot x.
all right, so let's skip number 2. I mean, you can do it if you want, but number 2, if I'm doing sine of x, where k is any positive number, and I'm going from negative k to k. So let's say it was here, negative k to k. What's your conjecture? So what is this value?
2.
Nope.
0.
0. Because it's not area, it's the integral, right? So it's going to take that negative piece and it's going to add it to the positive piece, and it's going to end up being 0. Yes? Yeah, Mackenzie?
Number 1, what 0.258?
Okay, make sure you're in radians, not degrees. Yeah. I almost messed that up myself. Okay, so compute the following integrals numerically. So if I'm going from -1 to 2, looks like it should be a pretty big positive number, right? This one never went below the x-axis, so you can actually go from 1 or -1 to 2, and it'll be fine.
When this is numerically, is that just when you use math 9?
And if it was a derivative, that means use n-deriv. So 2.043. Okay. Try the next one. So in your homework, I wrote, don't use fn int, so math 9, unless I allow it. So if I say that you can use it, then you can use it, but otherwise you shouldn't. You guys get 0.886 on the next one. All right, I don't know why my little thing's not writing, but I'll finish up this. So can I talk and you guys are okay with the other two? It's not writing anymore. So 0.886 was number 2. All right, and then compute the integral from 1 to 3 for the next one of f minus x squared dx. So how is this different than those last ones? Yeah, it goes below the axis. So what? So you can break it into the two pieces if you're actually finding the area, but you're not actually finding the area, right? You're finding the integral. So go from 1 to 3. So do it just like before. And then that wouldn't actually be the area, right? The area would be taking the part above and then subtracting out the negative number from below. What'd you guys get for your integral? -2/3.